In this example, we want to graph the quadratic function. Remember, a graph should have at least 5 accurate data points plotted to get the exact curve needed for these quadratic functions. Now, when you look at the function, you always want to ask yourself, what form is it written in? And so here we've got f of x equals 2x squared plus 12x plus 10. This function is written in standard form. And we know when we have functions in standard form, right now we need to put them into factored form, because if it's in factored form, we can locate the x-intercepts, use that as our foundation to build and find the turning point, your vertex, a table of values to create your graph, and then we can look at the other remaining key features. So how can we factor 2x squared plus 12x plus 10? Well, factoring should be just like we did before with expressions. Same idea if it's an equation. Just ignore the f of x equals. Does a greatest common factor exist? If you look at your terms, you can see there's a greatest common factor of 2. So if we divide that out, what are we left with? We've got x squared plus 6x plus 5. This is where you can think about your product sum pattern. What two numbers multiply together to give you 5, but add to give you 6? We can use a positive 1 and a positive 5. Now, some of you I know like going back and writing it as 4 terms, the unsimplified form of the one before that, because then you can look at it in pairs, divide out what they have in common to get your factors. Some of you are at the point where you can do that in your head already, or you already know what those factors are by looking at the remainder polynomial here, and you will end up with the same result. So again, let me show you both methods here. Your factored form would be 2 times x plus 1 times x plus 5. The first pair, you're dividing out a common factor of x. The second pair, you're dividing out a common factor of 5. So this is our factored form. Again, what can we do with factored forms? We take each factor and set them equal to 0 and solve. These values represent the x values of the x-intercepts. So I take x plus 1 and set it equal to 0, and I take x plus 5 and set it equal to 0. And we undo each equation. So how do you undo x plus 1? Well, we would subtract 1 from each side. How do you undo x plus 5? We would subtract 5 from each side. Therefore, x equals -1 and x equals -5. Those are the x values for your x-intercepts. So we could start plotting those points on our graph. We could write the locations and our key features. And we also can now start working on finding the turning point, the vertex, because it has to be in between the x-intercepts. So we want to say, well, what x value is between -5 and -1 on our number line? That value would be -3. So if that's the input, the question is, what output goes with it? Well, to find the output, we can take our -3 and put it either into the original function and evaluate it there, or some of you like to go to the factored form and evaluate there. You'll still get the same response. So if I substitute -3 in, what do we get out? Well, we get out a -8. And now we have the coordinates for our vertex, the turning point. So that's another point on our graph. Now remember, we want to build around these 3. So if that's our turning point, -3, 8, notice how there's still some input values that we don't know the output values of in between these x-intercepts and the vertex. So we might want to find their corresponding output so we can get our curve of our parabola a little bit better. We also could select values for x to the left of our x-intercept of -5 and to the right of the x-intercept of -1 to see how the curve would be behaving that way. So a sample idea of x values we could use would be perhaps maybe -4, -2. If you want to go outside of that, you could do -6, even 0. 0 might be a good one to do as well, because when 0 is your input, that's representing your y-intercept. So with whatever inputs you're choosing, again, you repeat the process of what you did before. You substitute them into your function and evaluate to find their corresponding outputs. So what outputs go with these inputs? Well, -4 and -2 give us outputs of -6. If we use the input of 0, we get an output of 10. Now, if you notice, we have lots of good data points left to complete at the minimum of 5 good data points to get the curve of our parabola, the graph of our quadratic function. And again, it should be a nice U shape. So all we have to do is to connect our data points because it is a continuous function. And then we can start looking at some more key features. And we said we already arrived at our y-intercept being at 0, 10. So we can record that. We also could talk about the axis of symmetry. Remember, the axis of symmetry is drawing the mirror that would be giving us the mirror image on each side. So that would go through our turning point. It would share the same input value. So we've got our equation of x equals -3. We could also talk about the concavity of our function. We can see our parabola is opening up. Again, why is it opening up? Our a value here of 2, right, the leading coefficient of 2, it's positive 2 times faster than it was before, reinforcing that it's concave up. We wouldn't even have to graph it to know that. Then could we talk about the domain? Now remember, the domain is the set of all the x values being used. So you look to the left and to the right to see how far you're able to go. And for our function, we know any input we use will get an output. So our domain, -infinity to +infinity, is being used, the set of all real numbers. The range, they're talking about the set of the outputs that are being used. So how low to how high. So you're looking how far down, how far up. Now, if you notice, we do have some restrictions here. The lowest we can go is -8 for the outputs, and that will continue on to +infinity. So using our interval notation, we've got our bracket, -8, comma, +infinity. So everything from -8, including -8 and above, would be part of our range.